Yeah, thanks. On the local Langlands categories. So starting from now, I will start to introduce the automorphic side of the categorical local Langlands. So, but for my talks, for simplicity, I will just, okay. I'll just assume our local fields to be QP. And I will indicate sometimes how to change things respectively to change to other fields, but you won't lose much. And I'll fix L different from P. So very roughly, our goal is the following. So we are interested in this category of smooth representations of GQP on, let's say, QR bar vector spaces. And to geometrize this, one can consider a suitable sheaf category on the classifying stack for this topological group. And the very naive and first proposal for the categorical local Langlands is that this category should embed into some sheaves on the stack of L parameters that are of quasi-coherent nature. But since if we have inner forms of G, so maybe, then their L groups are isomorphic. This means that they will have the same stack of parameters, which means that this inclusion cannot be an equivalence. And because if we have an embedding of the sheaf category for G, then there has to be an embedding of the sheaf category for G prime as well. So therefore, a basic goal to upgrade this even to a conjecture about the equivalence of categories is, we need to interpolate between classifying stacks for at least the inner forms of G. And then Kottwitz found that using G isocrystals, one could construct extended pure inner forms. And these are parameterized by the Kottwitz set BG. So parameterized by, and the geometrization, there are two geometrizations of this construction, and one due to Fargues using the stack of G bundles on the Fontaine curve, and this is bond G, and the other one is due to Xin-Wen-Zhu, and which uses essentially the moduli stack of G isocrystals on like perfect schemes. So these are, so basically the plan for these lectures is that in this talk I will explain the Kottwitz set, and then I'll explain bond G and isoc G in the next two lectures. So let's start now with isocrystals with G structure. So first about some definitions. Let's say R is a perfect FP algebra. Then we consider the width vector of R equipped with forbiddenness, lifting the forbiddenness on R. So if our base field is not QP, you can replace the width vectors by the ramified width vectors if your local field E is some finite extension of QP, or in equal characteristics, just the Laurent parser string, the parser string. And And so then an F isocrystal, or sometimes I'll just say isocrystal over R, is a pair V comma phi V, where V is a finite projective module over W of R with one, P inverted. And phi V is a Frobenius linear bijection on V. And morphisms between F isocrystals are just maps of V's that are compatible with phi. So we'll denote by isoc of R the category of isocrystals over R. And so because later we're going to use some Tannakian formalism, let me say that this is a QP linear exact tensor category, and it's idempotent complete. Okay, so very first example is when R is just FP bar, then we see that isocrystals over FP bar are just given by finite dimensional QP Breva vector space. So this is width vector of FP bar inverting P. And then this Frobenius on V. And since QP Breva vector spaces are just determined by their dimension, so we see that the set, once we fix a dimension of V, then the datum of this automorphism is given by QP Breva point of the group GLN. And if we classify them up to isomorphisms, then so at least objects in this category up to isomorphisms are given by GLN QP Breva modulo sigma conjugation. So namely, two elements in the QP Breva point of GLN are considered equivalent if and only if there is some element G such that G be sigma G inverse is B prime. Okay, so this result actually holds true for any algebraically closed field over FP, and this is known as the Dildon-Manning classification. So namely, the statement is that for any algebraically closed field over FP, isoc K is a abelian semisimple category with simple objects labeled by rational numbers, which are called slopes of these isocrystals. Where if you fix lambda to be S over R for some coprime integers R and S with R greater than 0, then the simple object V lambda is just the the r-dimensional QP-Breva vector space with the forbiddenness given by matrix of the form zeros everywhere else except for off-diagonals, and then here p to the s. Okay. So another example of an isocrystal is just the crystalline cohomology of family of algebraic varieties in characteristic P. So for example, if we have an abelian scheme over R, then one can take the first crystalline cohomology of A over the width vector of R, and then take invert P. Then this thing carries the forbiddenness induced by the absolute forbiddenness on A, and this gives an example of an isocrystal on R. And so then an isocrystal with G structure, or a G isocrystal over R, is then defined using Tannakian formalism, namely this is a QP linear exact tensor functor from the category of finite dimensional algebraic representations of G on QP vector spaces to isoc of R. And I will use the notation isoc G of R for the groupoid of G isocrystals. Okay, and and then the Cotwood set is just the set of isomorphism classes in this groupoid when R equals FB bar. So, and this can be described more concretely, so similar to what we've seen before, as the QP-Breva points of G modulo sigma conjugation. And the reason for this is that one has Steinberg's theorem, which tells us that G tossers over QP-Breva are all trivial. So again, you can classify these G isocrystals just by QP-Breva points of G modulo sigma conjugation. And then, so we said before that using elements in the Cotwood set, you can construct new reductive groups over QP. So in particular, fix an element B. You can define the reductive group GB by whose functor of points on QP algebras is just points in the QP-Breva tensor R points of G such that GB sigma G inverse is B. In other words, this is the sigma centralizer of the element B. And B is called basic if this group is actually an inner form. of G. And these are the extended pure inner forms. Okay, so I guess people are familiar with most of the stuff I said so far. So the next thing we want to do is to study the structure of this set. In particular, introduce the Newton maps, Newton map and Kottwitz map. So for this, let's give another interpretation of what BG is, using the Kottwitz gerbe. So to define this, let's observe that isoc FP bar is in fact Tannakian category, so which is QP linear, but it's not neutral in the sense that it has a fiber functor in some QP algebra, but it's not. It doesn't have a fiber functor over QP. So, so here it has a fiber functor over a QP breva. So, and concretely, the sentence just means that isoc FP bar is a QP linear rigid abelian tensor category with a faithful and exact tensor functor into QP breva vector spaces. Okay. And this fiber functor is clearly just forget the datum of the forbiddenness and remember this QP breva vector space. And so we're more familiar with the Tannakian formalism for neutral Tannakian categories, namely there is a fiber functor over the base. And in that case, one knows that the Tannakian category would be equivalent to the category of algebraic representations for some affine group scheme. And while for non-neutral Tannakian categories, the Lean has proven that there is a similar result, except that this will be equivalent to the category of representations for some gerbe. So, namely, the gerbe of fiber functors. So in this case, more concretely, this is the stack on QP algebras, sending R to just exact tensor functors from isoc FB bar to the category of vector bundles on R. And so the result of the Lean is that if you consider this gerbe of fiber functors, or this a priori just a functor, and this will be actually an affine gerbe over QP here. So namely, this is some FPQC sheaf of groupoids, which is locally non-empty, and then locally all the sections are isomorphic to each other. And affineness refers to the affineness of the band of the gerbe. But so, and in this concrete case, we'll call this the Kottwitz gerbe. For QP. Yeah. Sorry, the neutral means that the Tannakian category has a functor. So this category is QP linear, and if it would have a fiber functor over QP, then it's called neutral. Thanks for the question. Other questions? Okay. Right. So in general, the structure of a GERB might be complicated, but in this case, it's a result. In fact, already probably one can say due to Dodo-Nemani classification, but written this way, it's the theorem of Yakovenko, which says that this GERB is banded by some abelian group scheme, so the pro-torus D, which is the inverse limit of the multiplicative group over all finite extensions of QP, where the transition maps are just raising the parameter to the power of the degree of this finite extension. And so since this band is abelian, so one can also understand the statement that this is a GERB over QP as simply saying that this is a tosser for the FPQC topology under the classifying stack for D. So, and moreover, this GERB has some significance so at least when you consider the class of it, so let's say in the flat cohomology of QP was coefficient in D, so then this is given by the image of the fundamental class of local class field theory. So under the map.
So a question, what's that subscript H2 and L? Or?
Yeah, I was just saying that you can view this as the sheaf cohomology of D on the FPQC side of QP. So FR stands for flat. Okay. So, and it identifies with the image of the fundamental class via the following map. So Z hat isomorphic to H2 QP. So here you can take ℓ cohomology with coefficient in this inverse limit of roots of unity, mu n's. So here you have element 1, and then this group maps to, because each mu n maps to GM, and this n correspond to the degree of the finite extension, and you have a map from here to QP D, and the image of this map identifies with the class of the Kottwitz GERB. Okay, so what is the benefit of understanding it this way, or introducing the Kottwitz GERB? So lemma, so we can reinterpret the Kottwitz set BG as classifying G tossers on the Kottwitz GERB. So here, since G is smooth, so flat topology and ℓ topology are the same for computing G tossers, which is a result of Grothendieck. So I would just write H1 ℓ for this. And the result for this is, the reason for this is actually not too complicated, where you just write down. So, as I said, if you consider FPBF G tossers, which is the same as the tau ones, then using Tanakian formalism, you can interpret these H1 classes as considering exact tensor functors from algebraic representations of G to the category of vector bundles on the Kottwitz gerbe, and then modulo equivalences. So, and then the category of vector bundles on the Kottwitz gerbe is just by definition basically these isocrystals. So if you, so here, in fact, if you inspect on what we said before about our definition of BG carefully, then you can already draw the conclusion. But another way to draw the conclusion is to say that the category of isocrystals or vector bundles on the Kottwitz gerbe is also visibly the same as vector bundles on the quotient stack spec QP breve modulo Frobenius. And therefore, this H1 is also the same as H1 on this quotient stack. And then where again you use Steinberg's theorem to know that G tossers on spec QP breve are all trivial, so then the descent datum is classified by just a QP breve point of G modulo sigma conjugation. Okay, so maybe the reason I decided to tell you this is because I think this gives a very nice construction of the Newton map and the Kottwitz map. So this is again exploring the fact that we have this structure map from the Kottwitz gerbe to spec QP, which is a tosser under BD. So let's call this map F. Then we have a Leray spectral sequence for so maybe for G tossers along this map. So now G is not commutative, so a priori I only get, so in low degrees, a exact sequence of pointed sets. But at least I still have the statement that if I want to compute G tossers on the Kottwitz gerbe, then so the isomorphism classes here, this is the Kottwitz set BG, then it sits inside an exact sequence, again, of pointed sets, like this. So where the previous term is just a tau G tossers over QP, and then the next term is H0 on the tau side of QP with coefficient in R1 F lower star of G. And this push forward, you can compute by reducing to the case where this is a trivial tosser, that this is just the sheaf home from this protorus to G and modulo the adjoint action of G from the second factor. And and then this H0 you can also compute easily because this is the ℓ cohomology. So you can just take value of this sheaf over QP bar and then take Galois invariance. So, and then if you simplify this expression a bit, you realize that this is just a co-character group of G rationalized, and then modulo divide group action, and then take Galois invariance. So this is the co-character group of G, dominant part, and Q rationalized, and then take Galois invariance. So you end up with a map from BG to this thing, and this is the Newton map, which we'll denote by nu G. So let's make a remark here that you observe that if you do this construction, then you see when G equals GLN, then by Hubert-Knighty, you know that the H1 ℓ cohomology of QP with coefficients in GLN vanishes. So therefore, you draw the conclusion that in that case, the Newton map is an injection. Okay. But in general, you see that because of the kernel, which are also these actual pure inner forms of G, this Newton map does not completely characterize the Kottwitz set. So you would need another invariant, and Kottwitz introduced another map, kappa. And for this, let's again try to use this perspective of the Kottwitz chirp. So maybe I should say that I learned this construction from a paper of Fargues called G-tossers in p-adic Hodge theory. So namely, we can consider the following cross module, which is given by the datum of this natural map from the simply connected cover of the derived group of G to G. So where the action of G, so this datum of a cross module is such a map, and then an action of G on G as C, and this is given by just the adjoint action of G on its derived group, and then it lifts uniquely to the simply connected or the universal cover. Yeah. Yeah.
So for injectivity, I mean, this is a sequence of coordinate sets, I think. So is it clear that?
Oh yeah, that's a good point. Yeah, maybe. Yeah, sorry. Maybe I have to think about this. Yeah, but that's a good point. Maybe not. Oh, okay. Right. So yes. So the other fibers should be some twisted form of this. Yeah, great. Yeah, thanks for the question. Right. Right, so we consider this cross-module, and let's observe that, so this is actually quasi-isomorphic to another cross-modules, which just involve abelian groups, group schemes. So namely, we can fix some maximal torus of G, so not necessarily split, of course, and then take the pullback and call it TC, so just here. And you can compute or justify easily for yourself that this is actually a quasi-isomorphism, so namely induces isomorphisms on kernels and co-kernels. And then, so therefore, we get long-exact sequences from maps of cross-modules. We get long-exact sequences if we look at the cohomology of G as C and G on the Kottwitz-Gerb. So the first row, a priori, also only of pointed sets. But then similarly, we have long-exact sequences for the second row, which is genuine exact sequences of abelian groups.
Sorry, can you say what's a cross-module?
So basically, the datum of this map of groups, and then together with an action of G on the first one. So this is generalizing the notion of like a normal subgroup, and for which you can take a quotient. Right. But I guess this is more classical approach before like stacks and so on are popularized. But yeah. Right, so we know that the last term here is an isomorphism, and for the second row, there is a connecting homomorphism to H2 of the Kottwitz set with coefficient in T as C, and then Fargues showed that for any torus, the H2 of the Kottwitz-Gerb with coefficient in that torus is actually 0. So by essentially reducing to the case of a split gerb. So this is not too hard. And so this is almost what we want here, because so we're interested in the Kottwitz-Gerb, the Kottwitz set. It maps to this guy here, which is isomorphic to this guy here, and the next term is 0, so it identifies with the co-kernel of the first map in the second row. And now this is these H1s are the Kottwitz set for these tori, and Kottwitz showed that you can describe them, like for tori, you can describe them in terms of the Galois co-invariance in the co-character groups. And so similarly for T here, and then you realize that, that this co-kernel is precisely the Galois co-invariance in the algebraic fundamental group of G. So where this pi1 is just a co-kernel of this map from co-characters of TSC to that of T. And then you take Galois co-invariance. So therefore, you draw the conclusion that this group is isomorphic to the scalar coinvariance, and then now if you take the composite map, this is the Kottwitz map. We call it kappa G. So, and the result of Kottwitz is that so these two maps together is actually injective on the Kottwitz set. So the target and then second part is that so these basic elements that we introduced before, so the ones whose sigma centralizer gives inner forms of G, so these can be also now interpreted as those elements in BG for which the Newton point, so landing inside co-characters of G, is actually central. So if you restrict to these elements, then kappa G is an isomorphism onto the Galois coinvariance. Okay. So let me also remark that one can observe, again from this previous construction of the Newton map, that the kernel of the Newton map is identified with the H1 QP with coefficient in G, and so these are contained, of course, when the Newton point is trivial, then it's also central. So these are contained in the set of basic elements in BG. So, and these elements will give these group. So the GBs coming from elements in this set are actual inner forms. Actual pure inner forms of G, and this is the reason why we call those GBs coming from the Kottwitz set extended pure inner forms. And the second remark is that so the construction of kappa should actually reminds you of this exponential sequence. So namely, if G would be something like C star, then it has a universal cover given by C, and then the kernel of that exponential map is 2 pi I times the integers. And then this long exact sequence would land from H1 of C star into H2 with coefficient in Z, and that's boundary map is given the first Chern class of a line bundle. So this construction here is heuristically similar. So namely, this kappa G should be interpreted as some version of a first Chern class of a G bundle on the Kottwitz disturb. So if you read Fargues' paper, he basically discussed this construction of kappa G on the Fontaine curve. But it works similarly for the Kottwitz-Gerb. Okay. Okay. So the last thing I want to talk about is that once we have the construction of these two maps, one can define a partial order on the Kottwitz set, and then thus giving it a topology. So so if we have two elements in BG, then we say that B is less or equal to B prime if the Kottwitz point of B and B prime are the same, and the Newton point of B is smaller than B prime in the usual Brohat order. So namely, the difference between the two is a sum of positive co-roots with non-negative coefficients. So this defines a partial ordering, and then it has an attached order topology. Where the convention is that we say that B lies in the closure of B prime if B is less or equal to B prime in this partial ordering. Okay, so in the last several minutes, I will just give you two examples, draw some pictures, which are actually familiar ones. So in the first case, when G equals GL2, so we know that the Newton map is injective, so I will just draw the co-character plane of G. And then, so maybe spanned by some basis vectors. And then if we take the dominant part, this is taking maybe the positive co-root goes this direction, so I'm taking the part below this line, and then the image of the Newton map lies in some lattice points. If we rescale the co-character lattice by a half, so these are points in the image, so 0, 1, 0, 2, 0, and a half. And so similarly here, I have points this way, and then specialization relations goes like this. And then you can draw this picture too periodically in both directions. And then if we're interested in isocrystals coming from elliptic curves, then these will be corresponding to these 2 points under inside the Kottwitz set. Okay, so so in general for GLN, the elements in the Cotwitz set can also be described in terms of Newton polygons. And and for other groups, the simplest one is maybe symplectic group. You can just describe them again in terms of Newton polygons, but with the condition that they're symmetric. So maybe I'll just draw one example. Our G is SV4, and then so given some co-character, one can look at elements in the Cotwitz set that are bounded by this element. So basically, this in terms of Newton polygons, you look at polygons with the start and ending points being given. So here, 4. And then, so in this case, the set has 3 elements. So a mu ordinary element, which specializes to an intermediate element, and then specializes to one basic element. So, and these are given by, okay.
So maybe you want GSV4?
Okay, that's a good point, thanks. Let's do GSP4. Right. Right, so, and these 3 elements are given by polygons that looks like this. Basic element correspond to this isoclinic thing. And then the intermediate ones has 2 breakpoints. So here with slope 1, and then in the middle slope 1/2, and then slope 0. And then there's one mu ordinary thing, has 1 breaking point. It's here. Yeah, so as I said before, so in general, these are given by symmetric Newton polygons. Okay, I think that's roughly what I want to say.